we're going to look at a few more satellite orbits. We can generate any of these orbits using the same program that generated the space station orbit. What do we need to change in the program? Note that none of the properties of the physical space station, that is its mass or shape, entered into the orbit calculations. So the only change needed to the program is to change the initial values for the state variables, that is the initial position and velocity of the satellite. The program takes it from there. The global positioning system is maintained by an array of 24 satellites as shown in the graphic. The altitude of the array is 20,200 kilometers and the velocity of the satellites is 3.9 kilometers per second. So using those numbers we can generate the orbit shown in the graph. Geosynchronous satellites orbit the Earth once every sidereal day. Viewed from the Earth, a geosynchronous satellite appears to trace out the same path in the sky every day. A geosynchronous orbit in the equatorial plane results in a satellite that appears to be stationary in the sky, and that's called a geostationary satellite. The duration of a solar day is 24 hours, and that is from high noon to high noon. However, since in that 24 hours the Earth has moved relative to the Sun, it's necessary for the Earth to rotate slightly more than 360 degrees on its axis to complete the solar day. A sidereal day is the time it takes the Earth to rotate 360 degrees on its axis, and that is 23 hours, 56 minutes, and 4 seconds. We can compute the orbit of the Moon around the Earth using the initial conditions shown. Just as we had the solar day and the sidereal day, we have the synodic period of the Moon, which is the time from full moon to full moon, and the sidereal period of the Moon, that is the time it takes the Moon to circle the Earth as viewed from inertial space, and that is 27.3 days. We can use the same program to compute the Earth's orbit around the Sun by replacing the mass of the Earth with the mass of the Sun and using the initial position and velocity values shown. We will use the Moon orbit and Earth orbit sims in the next two projects. In the last lesson we computed the space station orbit. Let's see what happens when we change the initial velocity of the orbit. The first graph shows the space station orbit with an initial altitude of 402 kilometers and an initial velocity of 7.7 kilometers per second. This gives us an approximately circular orbit. The second graph shows the result of increasing the initial velocity to 10 kilometers per second with the satellite being launched from the 12 o'clock position. This gives us an elliptical orbit. The third graph shows a trajectory with the initial velocity increased to 14 kilometers per second. In this case, the satellite escapes the Earth's gravity and follows a parabolic or hyperbolic trajectory away from the Earth. Starting with a circular orbit and increasing the initial velocity results first in an ellipse that becomes bigger and bigger as the initial velocity is increased, until the point where the satellite just barely escapes the Earth's gravity and has a parabolic shape. Increasing the velocity beyond that results in a hyperbolic trajectory. So we have seen circular and elliptical orbits and parabolic, hyperbolic trajectories. What other types of orbits are there? Answer, none. We computed orbits and trajectories that are approximations to solutions to the differential equation p double prime equals g times m divided by p squared. What is the analytic solution to this differential equation? Answer, there is none. That is, we cannot write down a mathematical expression that evaluates P of t and that makes the differential equation true. We can approximate solutions to the differential equation as we have seen, but we can't write down a single expression that evaluates the solution. So we say that the differential equation does not have an analytic solution. Most differential equations that you encounter in physics and engineering don't have analytic solutions. That is why computational methods have become predominant in science and engineering. So the question is, without an analytic solution, how was Newton able to characterize the shapes of the solutions to the differential equation? Answer: it wasn't easy, and high-powered analytic calculus comes into play. We showed how the 2D differential equation for the two-body problem can be written in terms of the x and y coordinates. It can also be written in terms of polar coordinates r and theta. While the differential equation written in polar coordinates still cannot be solved analytically, a function relating r and theta can be derived, and that function is shown. R of theta equals h squared divided by g times m times 1 over 1 minus e cosine theta, where h is a size parameter for the orbit and e is a shape parameter. See the class notes linked below for a derivation of this relationship. The orbit shapes are determined by the shape parameter and correspond to the values shown for e. E equals 0, e less than 1 equals 1, and e greater than 1. These shapes are the conic sections, which are circles, ellipses, parabolas, and hyperbolas, called conic sections because they are the shapes formed when a plane intersects a cone, as shown in the diagram. Every solution to the two-body problem is one of these shapes. What if Newton had been wrong about gravity, and instead gravity was really a constant force, that is, the simple model we started with? What would orbits look like with constant gravity? Just for fun, let's find out. All you need to do is replace Newton's formula for gravity in the space station sim with -10 for constant gravity, and start the simulation with an initial position and velocity not corresponding to a circular orbit, and you'll get a result like the one shown. This lesson's assignment, number 1, generate the moon's orbit around the Earth. This program will be the basis for our next project, generating the Apollo trajectory. Number 2, generate the Earth's orbit around the Sun. This program will be the basis for our project after Apollo, generating the Juno trajectory. Thus far, we have modeled smaller bodies orbiting around much larger bodies, and we have ignored the insignificant motion of the larger body. We can just as easily model two bodies of comparable size orbiting their common center of mass, as shown. We have the outline for this program. Programs with astronomical numbers are difficult to debug, and we wanted easy numbers, starting with the gravitational constant. So we started with g equals 10 and tried various values from there. Also note that the subinterval length is small, which turned out to be necessary to generate accurate solutions. This page is the initialization code. I suggest you stop the video and peruse the outline for a moment. The rest of the program follows. This is the loop that advances the positions and velocities of both objects. Note that gravity pulls each body toward the other and is directed along a line between the two bodies. So you need to calculate the x and y components of the line connecting M2 to M1 and the distance between M1 and M2, which is r. Then use Newton's formula to calculate the force of gravity. Since the line goes from M2 to M1, the gravitational force is positive on M2 and negative on M1. Also note that it must be resolved into x and y components using xd, yd, and r. This code prints the graph. You can experiment with various values of g, the gravitational constant. With g equal 10, we get a parabolic, hyperbolic shaped trajectory. With g equals 20, we get circular orbits. Higher values of g produce elliptical orbits. I encountered the final graph very early in debugging and recognized that the orbits didn't have the right shapes, i.e. they weren't circular, elliptical, or parabolic, hyperbolic. So there was a problem. It was fixed by reducing the value of dt, which improved the accuracy of the solutions.